our presentation is about developing a relative Liutex-based subgrid model for bounded flows. So first, let me start with some background on large ID simulation. And as many of you know, LES is a computational approach that specially filters the flow field using a low pass filter, essentially separating large ID containing IDs from smaller scales. While LES resolves these large IDs directly, it models the subgrid scale motions using subgrid scale models. However, LES does have its limitations. The main challenge is the higher computational cost compared to the RAS approaches, and it requires fine mesh resolution and small time steps to capture the relative physics accurately. And in this slide shows the LES governing equations. The mathematical foundation of LES lies in the filtered incompressible Navier-Stokes equations shown here. And the key term in this subgrid scale stress tensor tau ij, which encapsulates the effects of unresolved scales and requires a suitable closure model. And according to the Busnitsky assumption, we can relate this stress tensor to the strain rate tensor through an ID viscosity. And this is where our subgrid scale model comes into play, determining the appropriate ID viscosity for the unresolved scales. In this slide, so before we introducing our model, let's briefly review the evolution of current subgrid models. And the first subgrid model was proposed in 1963, and that's the subgrid model. And in this model, there are three important parameters in the formula. The model coefficient CS, the long scale dirt, and the velocity scale. And in subgrid model, the velocity scale is derived from Sij. And for this model, the model coefficient is a constant. And so then in 1991, the dynamic subgrid model was proposed. And in this model, the model coefficient is not a constant. And this CS can be computed based on the local flow state. And then in 1999, the wheel model was proposed. And in this model, has a constant model coefficient, but the velocity scale is a little bit complex. And then another popular subgrid model is the Varimax model. And most recently, the Liutex-based subgrid model was proposed. And in this subgrid model, it has a constant model coefficient and a long scale, and they use the magnitude of Liutex as the velocity scale. And in this slide, this slide is about the Liutex-based subgrid model, and this model was proposed in 2022. And for this Liutex-based model, and it was published by Ding, Yuan, and Wang in the Journal of Hydrodynamics, and they used this simple form. The ID viscosity equals CR times dirt squared times R, where R is the magnitude of the Liutex vector. And their work validated the model on two test cases. The one is the homogeneous isotopic turbulence, and the other is the fully developed channel flow. And as you can see from these two figures, the model provides accurate eddy viscosity distribution near the wall, and which is crucial for the wall-bounded flows. And this was a significant advancement because it shows that Liutex could serve as an effective velocity scale in subgrid modeling. And then this slide shows our relative Liutex-based subgrid model. And our contribution extends this framework to what we call the relative Liutex-based subgrid model. And the key difference is in how we calculate the model coefficient and the long scale. We use this explicit formula developed by Wang, which incorporates three key flow features. And first, omega is the vorticity vector, and R is the real eigenvector of velocity gradient, and lambda Ci is the imaginary part of the complex conjugate eigenvalue of velocity gradient. And this formula captures the grid rotation component of fluid motion more accurately than previous approaches. And then in this slide, a crucial innovation in our model is the model coefficient CR, which determines the subgrid long scale. Unlike the Germano-Lilly coefficient, which is mathematically derived and performs well only for the Smagorinsky model. And here, CR is CR is dynamically calculated based on physical mechanisms of the actual flow. And this figure shows the concept. In each computational cell, you have eddies of different sizes. And CR represents the friction of the cell size that corresponds to the average eddy size that should be modeled at the subgrid scale. And this physical basis makes our model more adaptable to different flow conditions. And then let me explain our subgrid long scale in more detail. We calculated based on the local flow state using this formula that R equals 2 times the maximum of the cross product between the unit vector of Liutex and the vector formed by the cell center and the phase center. And this figure shows the geometry. We are essentially finding the maximum characteristic length that represents the vertical structure within the cell. And this is fundamentally different from other approaches that base the long scale primarily on cell dimensions. And we will also compare three different long scale here. The maximum cell length among three edges, the cube root of cell volume, and our Liutex-based long scale that are. And you can see how they are different and how they differ significantly depending on the flow characteristics. In this slide, let me describe our numerical implementation. And we are using OpenFOAM with second-order background, temporal discretization, and linear interpolation for momentum fluxes. And for the subgrid scale turbulent kinematic energy, we use TVD schemes. And for the computational domain, our computational domain is 12.8 meters by 2 meters by 4.8 meters, which simulates channel flow at a friction Reynolds number of 544. And we tested 3 grid resolutions with the total grid numbers ranging from about 1 million to 10.6 million cells. And these figures show the medium grid resolution and an instantaneous snapshot of the streamwise velocity scale or velocity field. It shows the turbulent structures we are resolving. And then this slide has 4 figures which shows the 3 components and magnitude of the Liutex vector field. And what's important to understand is that the Liutex vector is an advanced vortex identification method, which can provide both directional information and vertical structures and quantify the local angular speed of the rigid rotation component of the fluid motion. And this makes it an ideal basis for an subgrid model because it captures the essential physics of turbulent eddies that need to be modeled. And then this slide, here is a crucial comparison of different long scale. We are showing dimensionless ratios here, dirt max over dirt x and dirt volume over dirt x and dirt r over dirt x. And what you can see is that dirt r, which is our Liutex-based long scale, shows a significant spatial variation that correlates with the actual flow structures. But in contrast, the other long scales like maximum cell length and the cube root of volume are more uniform and don't respond as dynamically to local flow conditions. And this adaptive behavior is one of the key advantages of our approach. The model can automatically adjust to local turbulent characteristics. And then in this slide, we present a comparison between our current dynamic model coefficient CR and the classical Germano-Lilly dynamic model coefficient CD. And as you can see from these 2 figures, the Germano-Lilly model coefficient shown in figure B produces significantly larger values compared to our CR coefficient in figure A. And this difference in magnitude has important implications for the predicted eddy viscosity and the overall behavior in LES simulations. And now let's look at the performance. These plots compare Reynolds shear stress predictions from different subgrid models against the DNS data. For a current model, it is shown in red, and it performs better than both the dynamic Smagrigsky model and the once original model. And as we move from coarse grid to medium grid resolution, the difference between different subgrid models becomes quite small. But our current model still shows a slight improvement. And this demonstrates that our model maintains accuracy across different grid resolutions. And it is essential for practical LES applications. And then in this slide, let me show some normal stress and shear stress components. For normal stress, on the left, you can see our current model performs better than once rigid model, especially in capturing the peak over the wall and the correct decay rate moving toward the center line. And in figure B, for shear stress on the right, again, our model shows improvement, particularly in the near wall region, where accurate prediction is most challenging. And these results confirm that our model provides reliable predictions for the critical renal stress components in wall-bounded turbulent flows. This slide shows the computational speed. An important consideration for any subgrid model is computational efficiency. And these two tables shows the computational speed comparison using 128 cores. And our current model with the CR coefficient is faster than original one's model using the Germano-Lilly coefficient, only about 4.21%, slower than the reference case compared to 6.89%. And what's better is that if we implement dirt arc calculation more efficiently by integrate it directly with the subgrid scale model computation rather than recalculating, we can make it even faster. So, and when compared against other classical subgrid models in the second table, our model's computational cost is competitive, is actually faster than the dynamics Magrinsky model with Germano-Lilly coefficient. To conclude, we have successfully developed a relative Liutex-based subgrid model for LES simulations. And the key innovations are, first, we use the Liutex as the velocity scale in the subgrid model. And second, introducing a Liutex-based long scale that depends on both a cell size and local flow state. And third, using relative Liutex as a dynamic model coefficient. And fourth, achieving a competitive computational cost compared to other popular subgrid models. For future work, we plan to compare our model against more subgrid models beyond what we have shown today. And more importantly, we want to validate the model's effectiveness on more complex engineering cases. I mean, real-world geometries and flow conditions to demonstrate its practical applications. So that's all for my presentation. Thank you for your attention.